In this lecture, we're going to go over the fundamentals of specific rate. And the goals for the lecture are to understand how to design a best case theoretical biocatalyst or a magical catalyst. Understand the concept of a rate constant. Understand how to convert an enzyme's kcat to a velocity or specific activity. And understand how to go from fermentation volumetric rates to specific activities. So the goal of the lecture is to be able to understand how to go from an enzyme parameter like a kcat to the volumetric rate in a fermentation. So remember, the volumetric rate is how much product you make per liter per hour in the tank, in the fermenter tank. And we want to be able to go from that back to an enzyme parameter and back and forth, right? This would be the enzyme that is producing the product. So if the product is an enzyme, it would not be that enzyme. It would be the enzymes or the enzyme systems that are making the product. So we first go from a kcat or a kinetic parameter for an enzyme to a specific activity or a Vmax. That's how active each enzyme is or molecule of enzyme is. The expression level, which is how much of that enzyme you express in your cell, translates to the ideal whole cell enzyme activity or whole cell enzyme activity, which is how good that lysate is, the cell's lysate or the cell itself is, at making your product. That can be converted from an enzyme unit. So this would be micromoles per minute per milligram or other units of biochemistry to specific rate, which would be a unit of productivity. So moles to grams, basically. And then the specific rate, which is how good each cell is, translates to the volumetric rate based on how much biomass you have, so how many cells you have, right? Now, the nomenclature can get really confusing, and some people find this lecture difficult because they switch the nomenclature around. So just to be really clear, the specific rate or the specific productivity in today's lecture, we're going to talk about the fundamentals of specific rate, with some key goals being to understand how to design a best case theoretical magical biocatalyst to convert substrates to products. Understand the concept of a rate constant, understand how to convert an enzyme's kcat to a velocity or specific activity, and understand how to go from fermentation volumetric rates to specific activity. So the goal in discussing specific rate is really to be able to transition from an enzyme parameter to a volumetric parameter in a fermenter. So we want to be able to get from a kcat, how good an enzyme is, to how much you're going to make in a tank. Right? This enzyme would be the enzyme that produces your product, right? And this would be a magical enzyme that does all the conversions, is how we're going to model it today. But these are the enzymes that make your product. If your product is an enzyme, it's not the kinetics of that enzyme, it's the kinetics of the enzymes making your product, right? So we first go from a kinetic parameter like a kcat to a specific activity or a Vmax. This is how good your enzyme is per milligram of enzyme. The expression level, how much of that enzyme you have in your cell, gives you how good your lysate is or how good the cells are from a biochemical standpoint. So the activity per cell lysate. We then convert the activity, how good each cell is, so the whole cell enzyme activity, to a specific rate, converting from basically this. What this does is it converts from biochemistry units to productivity units, so micromoles to grams. And then we go, this is how good each of the cells are at making the product, and then how many of the cells you have, the biomass level dictates your volumetric rate. So before we dig into an example of this, it's really important to keep track of the nomenclature. Some of the reasons why this lecture can be confusing is because we use the term specific a lot. So just to clarify, that specific rate or specific productivity are used interchangeably in the field, and they are per cell metrics. So this is how good your product is per cell, so gram per gram dry cell weight, right? Activity, the term specific activity, is in per enzyme metric. So that's kind of equivalent to a Vmax or a whole cell enzyme activity, right? So although they both have specific in the title, they are different. Specific rate or specific productivity is per cell, and specific activity is per enzyme. So if you haven't reviewed the lecture and the videos on Michaelis-Menten, I would highly recommend stopping now and reviewing this video on how the Michaelis-Menten equation is derived. But to review that, the velocity of the enzyme reaction is equal to the Vmax, which is the saturating kinetics, times the substrate concentration divided by the binding affinity, or Km, plus the substrate concentration. So if you increase the substrate of the enzyme, you will increase the initial velocity until you hit the maximal point. The Km is an estimate of how good the enzyme is at basically binding the substrate. So if the lower the Km, the lower the substrate you would saturate the curve at. Now, we're going to put these enzymes into a magical theoretical biocatalyst, right? And this construct is really good for understanding some basic concepts of engineering biology and engineering bioconversions or biosynthesis with enzymes. But there are many, many reasons why you would never actually have a magical theoretical biocatalyst in real life. But we're going to use it in this lecture as a construct. So we have a cell. And in that cell, we have a lot of cellular enzymes, right? And our magical theoretical biocatalyst is this cell that expresses a single enzyme, which is this blue enzyme, which converts your substrates to your product, right? So in the real world, you may have a product that requires multiple enzymatic steps to go from substrate to product. But in this case, we're condensing everything down to a single theoretical enzyme that magically convert whatever substrate you want to the product that you want. Now again, to clarify, if your product is a protein or is an enzyme, the blue enzyme is not the enzyme that is the product, it's the enzyme that makes the product, right? So if this was, for example, a monoclonal antibody, this would be the ribosome, right? So this is the catalytic machinery that makes your product, even if your product is a protein. So the single theoretical enzyme in blue is capable of converting magically all your substrates into the desired product, right? This helps with yield calculations as well as rate calculations. So let's look at a sample problem. So what is the required specific activity for an enzyme? So that's basically how good is this enzyme needed in an ideal bioconversion process to make your product and achieve an average volumetric rate of 10 gram per liter per hour, right? So we're saying basically if we have a cell, how good does this blue enzyme need to be to make the product at 10 gram per liter per hour? So the change in product over time is the volumetric rate, is given that 10 gram per liter per hour. We know that the volumetric rate is the specific productivity or specific rate times the biomass level, right? So we need to estimate or know a biomass level to be able to calculate the specific productivity or vice versa. So we're not given that in the problem, but we can assume a given biomass level, and for this sake, we're going to assume 50 grams dry cell weight. So the volumetric rate is gram per liter per hour. The specific productivity is gram per gram cell dry weight per hour, and the biomass level is gram cell dry weight per liter. These cancel out. And if we assume 50 grams dry cell weight per liter of biomass, which is a reasonable assumption, then the specific productivity we need to hit this target of 10 gram per liter per hour is 0.2 grams per gram dry cell weight per hour. And we know from our previous lectures that specific productivity is equal to the whole cell enzyme activity times 500 milligrams of total protein per gram dry cell weight. So this is just basically the protein concentration per gram dry cell weight, because we know that 50% of the dry cell weight of most cells is protein. So the specific productivity that we just solved on the previous slide is equal to the whole cell enzyme activity times this conversion factor. We can cancel out those units and we end up getting 0.2 divided by 500. And then the units in this right now are grams per milligram of total protein per hour. Now, when we're converting from whole cell enzyme activity to specific rate, this is the step at which we do the conversion from production metrics like gram per liter per hour to biochemical units. And so whole cell enzyme activity is not usually given in grams per milligram of protein per hour. It's given in micromoles per minute per milligram of protein, right? So we need to convert this. And so this number is 0.004. Now we have grams per milligram of total protein per hour. Then we can convert the hours to minutes. So 1 hour, 60 minutes. And then we need to know, in this case, the molecular weight of the product to be able to convert from grams to moles. So, and then we have 10 to the 6 micromole per mole, right? This will give us the right units for the whole cell enzyme activity. So we can assume in this case we weren't given it in the problem, and it would be dependent on the product you're trying to make, but we can assume that the molecular weight, to make the math easy, is 100 grams per mole. So if we plug these numbers in and cancel out the units, we end up with a whole cell enzyme activity of 0.0667 micromoles per milligram of total protein per minute. So this is a traditional biochemistry unit of units. 1 unit equals 1 micromole per minute per milligram. So from previous lectures, we know that the whole cell enzyme activity is equal to the specific activity. So this is how good the lysate is, or how good the cell guts are at making your protein or making your product of interest. And this would be how good the enzyme is, right? So this, how good the enzyme is, times the expression level, or how much of the enzyme you have inside the cell, gives you your whole cell enzyme activity. Or, rearranging, the specific activity is equal to the whole cell enzyme activity divided by the expression level. So if we have 0.0667, right, the other assumption we need to make, which we weren't given in the problem, is how good are we expressing this protein, right? What is our expression level? If we assume an expression level, that would be 1%, which is usually pretty obtainable. So a pretty easy expression level where we have 1 milligram of target protein per every 100 milligrams of total protein on 1% expression level. We can plug that in and calculate the specific activity required, which would be 6.67 micromoles of your product per milligram of the target protein, or the magical theoretical protein, per minute. Right? So that is how we go from a volumetric productivity to a specific activity. So this is how good the magical theoretical enzyme needs to be, right? We had to assume or know the molecular weight of the product. We had to assume or know an expression level of the blue protein. And we also had to know or estimate a biomass level in the final fermentation. So it's important at this point to revisit the nomenclature again, because it can be confusing in the literature what is a unit and what is specific activity. So we went through this before in a previous lecture, but we'll revisit it again now. So the ideal, or the whole cell enzyme activity, or the ideal whole cell enzyme activity, is the activity per milligram of total protein, right? So this is the amount of product made by an enzyme per minute normalized to the total amount of protein in the cell. And again, this can be estimated by performing biochemical assays on whole cell lysates without the purification of the desired protein. This is how good the lysate, or the cell goo, or the cell guts are at making your product. Specific activity, however, gets a little confusing, because we've been using it here as a definition of the activity for a purified protein. And that is how I tend to use it, and that's what we'll use it in this course. And so in our case, specific activity would be more equivalent to a Vmax. But why it's called specific is because specific activity is the activity in a mixture that is specific to the enzyme of interest. And this is a legacy term that came through the field of biochemistry as people were purifying enzymes and tracking the enzyme activity that was specific to their reaction, right? It's an old term and concept. And so basically what they would do is they would take a cell lysate and they would begin to purify through different means the enzyme that they wanted, and they would know how they were enriching by measuring the activity of, in this case, the red protein, right? So they would go through different purification steps and keep measuring the activity, right? So if they were measuring the activity of the red protein in this total cell lysate, it would be the whole cell enzyme activity. And then they would use different steps of purification, and they would end up with a mostly purified protein at the end that would be given a specific activity. But you also, during this time, usually lose a lot of the protein of interest, right? And so you'll see papers like this, right, where they track the specific activity through the purification, right? So they basically do different procedures and they track the activity that is specific to that reaction, right? And in this case, they would have a yield loss. So they start with 100% of the protein in the whole cell enzyme activity, or in the lysate. And then by the time they go through their purification steps, they have a relatively pure protein, but they've lost a lot of it. So this is going from a whole cell enzyme activity to a Vmax, or specific activity. And in this course, I tend to equate specific activity or I will equate specific activity with the Vmax, which is the activity of the purified protein. But if you read the literature, you may see the term used for any of these values. So specific activity in units is micromoles per minute of milligram protein. I will use this term to be equivalent to Vmax, which is micromoles per minute per milligram of purified protein. And whole cell enzyme activity is a specific activity when we're talking about total protein. So how do we go from Vmax to a kcat? So the problem is when you've seen Vmaxes before, and what you saw on the previous slides with the Michaelis-Menten curve is you'll see a Vmax equal to micromoles per minute. So it's a rate of product per minute. This is what you learn in biochemistry class. This is what we need to do in biochemical engineering to be able to directly relate the kcat and translate it into units that we can use where we can convert the kcat to a specific activity or whole cell enzyme activity. So what we need, the difference here would be this is micromoles per minute per milligram of purified protein, whereas in biochem class you probably heard micromoles per minute. Now I'm going to convince you that they're basically the same, and we've just been canceling out units that really should not be canceled out. So if we talk about Vmax, right, it's pretty obvious to think about measuring in a test tube the velocity of an enzyme reaction. So we add reaction to the test tube, right? We have substrate equals 0, so there'll be no reaction, and then we increase the concentration of substrate with a given amount of enzyme, and there's one enzyme concentration, and we'll get a curve like this, right? So this will be Vmax, and the half Vmax will be the Km, right? And this is probably how you're familiar with thinking about stuff. But what happens if you just double the amount of enzyme that you add to the reaction? If you double the amount of enzyme that you add to this reaction, you will get twice as much of a Vmax, right? The Km will stay the same, meaning you'll get half the Vmax too, will still be at the same point, but your Vmax will increase, right? And this is because this velocity is not just a function of the substrate concentration, but it's a function also of the amount of enzyme you add to the reaction, right? So it's actually a function of micromoles per minute per milligram of protein. And it's important to include that per milligram of protein to be able to do the unit cancellations later on. If we add 2x the enzyme, we get 2x the Vmax. Vmax is a function of enzyme concentration. And this is actually where kcat comes from. Kcat is Vmax per enzyme, right? So although kcat units are per time, it's actually the Vmax per enzyme, and the moles cancel out, and we'll go through that in a second. So to engineer the system, though, we need to be able to change the enzyme levels. So we need to be able to keep track of how much enzyme we have. We can't just cancel it out, because that's actually what we're able to change in the system to be able to increase the rate, right? We increase expression, we increase enzyme. So this is why in this analysis, we're doing a more precise definition of Vmax. So kcat, usually you get the nomenclature or the units per second. But really, it starts off as moles of product per moles of enzyme per time, right? And people tend to cancel out mole per mole, right? So mole of product per mole of enzyme, and the moles cancel and you get per second. But they're not keeping track of what mole is of what. So the numerator is a mole of product, and the denominator is a mole of enzyme, right? You can argue this is correct or not correct, and I'm not going to get into that argument, but this is the standard nomenclature. But if you just have per second and you miss moles of product and moles of enzyme, you can't really go from a kcat to a Vmax or a specific rate, right? Or it's more difficult to remember how to do it. So how do we go from kcat to Vmax? If we keep in mind that the kcat really is moles of product per moles of enzyme per second, and we want to end up with grams of product per gram dry cell weight per hour or some other production metric, then we have to know the molecular weight of the enzyme, right? So that is what's missing a lot of times when you're interconverting a specific activity or a Vmax to a kcat is the molecular weight of the enzyme. So the moles of product per the mole of enzyme per time, then we need the mole of enzyme per milligram of enzyme, right? And then we can do second time conversions. This happens to be 1,000 divided, the molecular weight of enzyme divided by 1,000, or inverse of that, 1,000 divided molecular weight of enzyme. And so the Vmax is 60 times 10 to the 6 micromoles of product per milligram of enzyme that's purified per minute, right? So this calculation can be done. So you need to either know the molecular weight of the enzyme that you're using, or you can estimate the molecular weight of an enzyme. By default, I tend to use, if I'm doing planning stages, 50 kilodaltons as the molecular weight of the enzyme. hopefully this makes sense, because you need to be able to estimate you need to be able to know how much enzyme you have to be able to get a milligram in the bottom of enzyme in the denominator. You need to be able to know this math. So now you should know how to relate the kcat to the target rates, right? So we can go from kcat, which we just did. We can use that knowing the molecular weight of the protein or the enzyme. The kilodaltons of the enzyme is needed to go from kcat to Vmax, or specific activity. The expression level takes you from specific activity to ideal whole cell enzyme activity or whole cell enzyme activity. Then it's just unit conversions, where we need to know the molecular weight of the product to go from the whole cell enzyme activity to the specific rate. And then we can go from the specific rate to the volumetric rate knowing the biomass level. This is the nomenclature can make a lot of this very confusing, but in general it should be pretty simple if you just walk through it a few times. And this way you can actually design how well your fermentation will be given a certain kcat and expression level, or you can say what would be the needed enzyme kcat for a particular volumetric rate.